Suppose that we have two positive charges Q1 and Q2 separated by a distance r. Q2 will exert a force F on Q1, and Q1, according to Newton's third law, will exert a force of equal magnitude and opposite direction on Q2. The force F is the electrostatic force, and in this case it is repulsive because the two charges are alike. If one of the charges, however, is negative and the other is positive, then the force will be attractive. The electrostatic force is given by F equals kq1 q2 over r squared, where k is Coulomb's constant. Note that if the charges are kept constant, then the force is inversely proportional to the square of the separation distance. In part 1 of the experiment, the two charges will be kept constant and equal to each other, and the force is measured for various separation distances. After that, you will plot a graph of F versus R and another graph of F versus 1 over r squared. Be sure to add the correct fitting to each of the graphs. In part 2 of the experiment, Faraday's ice pail will be used to measure the charge quantitatively. Faraday's ice pail is connected to a charge sensor, which is connected to the 850 universal interface, so you can get the reading of the charge sensor from your computer screen. If you have two charges, let's say two positive charges, for example, Q1 and Q2. This distance represents the distance r. The force is can be thought of as the force acting on Q2 by Q1, which is in this direction, or the force acting on Q1 by Q2 in this direction. We will use this apparatus to study the relation between the force and the distance, the separation between the two charges. So for this purpose, the distance r can be measured using this scale. Notice when the two balls barely touch each other, like this, the reading here is 2.8 centimeters. And the reason is that we have a radius of 1.9 centimeter for each of the two spheres. 1.9 plus 1.9 is 2.8, and this is the separation, the minimum separation between the two spheres. Okay, so this is an indication of the distance r in the equation. All right, the amount of charge Q1 and Q2 is going to be equal, and the reason is that we will use the same power supply to charge both spheres with the same magnitude and sign of the charge. Okay, so both of them will have a positive charge. We have two spheres here. One can be slided back and forth, and the other one is hanging from this very delicate wire right here. Now this wire acts like a torsion spring. So if I move the sphere out of equilibrium, it's going to come back to its equilibrium position, because it is very similar to a linear spring, but this is called a torsion spring. So the magnitude of the force from the spring is proportional to the rotation angle of this sphere right here. Okay. So as a measure of this force, to measure the force, we will be measuring the torsion angle, the angle by which we rotate the spring, as we will explain later when we start doing the experiment. Now this magnet here, there are a pair of magnets here. These are used to dampen the oscillations, because without these, it's going to take a very long time for the sphere to stop. Now to understand how they work, notice how when I remove them, the sphere will travel more and it will spend more time until it starts. Now, to learn more about this, you can search for eddy currents and how they work, because this is the concept by which this sphere is being stopped. Now, notice that when the sphere is at equilibrium position, these two marks line up. Okay? When it comes back to equilibrium position, they will line up to tell you that the sphere is in equilibrium position. If they are not lining up, this means that we need to do some adjustments to this apparatus by rotating this part of the spring, which is the wire in this case. All right. So the two spheres will be charged with an equal amount of charge, and then we will set the separation between the two spheres and read it from here, from the scale. Now, when the two spheres have charges, there will be a repulsion. Now, this sphere is fixed at place, so the other one will move away. So there will be a force from the first sphere on the second that will move it away from the first sphere. To return the sphere to its equilibrium position, we will rotate the spring to apply some spring force, which is again proportional to the electrostatic force. The spring force will be equal in magnitude to the electrostatic force, but opposite in direction. And this what will bring the system back to equilibrium. So if we take the reading of the angle, which is, remember, is proportional to the force of the spring, this gives you an idea of how much electrostatic force we have, because remember, the two forces are equal in magnitude and opposite in direction. Before taking the first reading, we have to make sure that the system is calibrated and set up correctly. So when the two spheres touch each other, we want to make sure that the reading here is 2.8 centimeter, which is twice the radius of each sphere. And we want to make sure that the free sphere is hanging vertically. The two spheres barely touch each other. And when all of this is happening, of course, all of this occurs when the two spheres have zero charge on them. When all of this is satisfied, we want to make sure that the reading here is 0 degrees. So when there is 0 degree angle, there is zero force from the spring, and everything should be correct in this case. Now we will start to take the first reading. To do this, we will turn the power supply on and increase the voltage to 6,000 volts. We have to be very careful when we deal with this high voltage. Okay. Now, before charging the two spheres, I want to move this sphere away as far as I can to prevent any effect of inducing charges from one sphere on the other, because we want to make sure that the two spheres have exactly the same amount of charge. So I'm going to touch the first sphere. Notice that the spheres have conductive coating. So once you touch the sphere, you will displace a positive charge on that sphere. So touch the first one, touch the second one gently, turn this off quickly, and then move the sphere to a separation of 10 centimeters. Now, as we can see, there is repulsion between the two spheres, so we have to move quickly and search for the angle of torsion that gives you equilibrium. Okay, so I think this is the best angle, but we will repeat the reading 2 more times to make sure that we have the correct reading. Now, we will record this angle. So at a separation of 10 centimeters, we have an angle of 27 degrees or 28 degrees in this case. All right. Now I'm going to repeat the same reading a second time. So I'm going to move the sphere again away, touch both spheres to discharge them. Notice that I didn't bring this back to 0 because it's more accurate to start from where we stopped the previous time. So I'm going to turn this on, make sure we have 6 kilovolts, and then touch sphere 1, touch sphere 2, and then turn the power supply off, move to 10 centimeters. Let's double check all our work. Now we probably need to fine tune the angle. to make sure that the two marks line up. Remember, when the two marks line up like this, we are sure that the sphere is hanging straight. Now this is an angle of 31 degrees. Okay, so this is the second reading. I'm going to repeat for the third time. Move away, touch both spheres to neutralize them. Turn the power supply on. Now let's make sure we have 6 kilovolts again to ensure that we have the same charge. Touch the first one, touch the second one, turn off, and then move back to 10 centimeters. Okay, let's see if we need any fine tuning. Let's wait a little bit for the sphere to come back to equilibrium. And then we probably need 1 more degree here. I think this is enough. So we have an angle of 32 degrees, all right? In this part of the experiment, we will use the Faraday's cage to measure the amount of charge on the sphere. Okay. Now this Faraday's cage is connected to a charge sensor, which is connected to the interface that we will use throughout this semester. So basically, the reading of the sensor is transferred via this interface to the computer, and we will see the reading on the screen right here. Okay. Before we start, we will make sure that everything is discharged by touching everything, right? And also press the 0 button on the charge sensor. Now take a look at the reading now. It's times 10 to negative 5 microcoulomb, which is extremely small number, all right? Now I'm going to turn on the power supply to charge the sphere to the same voltage difference of 6,000 volts. Now I'm going to charge the sphere and then insert the sphere here. Now take a look at the reading. It says 0.012 microcoulomb. All right. Now let's reset everything. I'm going to repeat the same thing, but after resetting everything and touching this sphere with another one. Let's see how we will do it. So I'm going to charge it to the same voltage of 6,000 volts. All right. Now I'm going to touch the other identical sphere and then measure the charge again on our sphere, and we have a reading of 0.006 microcoulomb.